I hope you had your coffee, otherwise it could be quite hard to go through the day. By the way, I'm Giulia Calignano from University of Padova, and I'm very happy to talk about cognitive pupillometry. I start using this measure during my PhD at University of Trento, and then I continue use it during my postdoc at University of Padova together with Sofia Russo, that is now a PhD student candidate, finally. So, and yeah, I don't know if someone here has already some knowledge about pupillometry or some experience with it. Don't be shy. If you already use it, some study, raise your hand. Okay, cool. So maybe it won't be so, I hope not to be too boring for you guys. By the way, yeah, the main aim of this tutorial that aims to be very practice oriented and by using also the R software. And again, it's nice to know if someone here has also some experience with R. Nice users in the room, that's cool. So yeah, as you maybe noticed in the Open Science Framework repository, I uploaded both a dataset and a script, and we will go through it together, and maybe in the second part of the tutorial. By the way, the main aim of this tutorial is to mainly to disentangle the main doubts about cognitive pupillometry that should be intended as quite slightly different compared to pupillometry per se. So in a way, how to get use of pupillometry to get a cognitive interpretation of this measure, this index. So to fully understand the measure and therefore to avoid some very common methodological mistakes that are not so, that are common, and approaching this multiphasic measure. So I would like to start with very few information about the physiology and the psychology of pupillometry, just in order to understand in what sense I mean mistakes, methodological mistakes. So first of all, I just did a very brief search on PubMed using the keywords pupillometry or pupil size and psychology. And as you can see here, this measure has been used since a long time ago, 1972, but is now very used, and I mean its use has grown a lot in the last decades and seems to continue attract interests. The next thing is that at the very beginning of the history of this measure, let's say, the first authors projected the image of the pupil on the wall and measure variation of the diameter of quite good technologies like eye tracker that actually are not the best instrument to do a pupillometry study. I mean, eye tracker are mainly there for eye tracking studies. So to get measures like spatial coordination of the eyes, saccade latency, fixation, so on, are not the best instrument to do pupillometry. By the way, all eye trackers, or at least the main eye trackers we have in our laboratories, like for example, iLink, if you know it, or Toby, it's also very common, especially in developmental psychology, because it's easy to use and don't require infants to be, infants can move with Toby and etc. These instruments always collect the pupil diameter changes over time. So all eye tracker so far are able to get this measure from both eyes during any eye tracker study. Okay. So let's start with the physiology and psychology of this very nice measure. So as you may know, it's very brief here. We have the pupil, that is the black window at the center of the eye, and it's surrounded by the iris that can have different color, and the sclera. Basically, the pupil is a window for light. So it opens or closes, and its main function is not to tell us anything about cognition. The main aim of the pupil is just to allow the light to enter the eyes and reach the retina and blah blah blah, make us see and focus or etc. This pupil can, of course, dilate or constrict, and this is possible because of two main muscles: the dilator muscle and the constrictor muscle. Here, this is an adaptation of Matot and Matot 2022, and you can find this paper on the extra resources of the OSF repository. Yeah, I really recommend you to go through that paper because it's very detailed and give you a lot of very precise information. So we have seen these two main muscles, but they are quite different in terms of the neurobiology that manage their activity. As you can see, for example, the constriction pathway that mainly manage the constrictor muscle has many center that let's say communicate to make this muscle constrict, so the pupil constrict. When the pupil constrict, basically it's likely to have too much light, okay? And so in order to reduce the amount of light that enter in the eyes, the muscle respond and constrict the pupil. On the other side, and it's quite interesting for us as psychologists, the dilation muscle has quite a simple system that governs it. And it's quite clear that the dilation is mainly an index of the sympathetic activation. This is a sympathetic system. Indeed, the main centrum of the sympathetic activity is the locus coeruleus here. It is the main center that regulates the dilation of the pupil. That's why in the majority of cases we talk about pupil dilation instead of pupillometry. So to sum up, the dilator muscle is under the adrenergic control, that is the sympathetic system, and from the superior sympathetic ganglion. The sphincter pupillar, that is the Latin name of the constrictor muscle, is innervated by cholinergic fibers of the parasympathetic system. That, as you know, as psychophysiologists, the parasympathetic system is quite more complicated to disentangle in terms of functional interpretation in cognitive psychology compared to the sympathetic system. And an information that may be useful for you is that the typical size of the pupil is 3 to 5 millimeters. By the way, we can also collect extreme values that could range from 1 to 9 millimeters. And in the practice, in the hands-on R, we will deal with this degree of freedom. Because, you know, when you collect data, you can observe some extreme values that could be an error, an artifact, or not. And may you be interested in understand the impact of including or excluding those extreme values on your statistical results. This could be quite critical. Another information might be useful for developmental psychologists like you is that infants have a bigger pupil compared to adults. Indeed, the pupil gets smaller per year, and so but pay attention that this does not mean that the effect of dilation is higher. Okay, the dynamics of pupil dilation are quite similar independently from the developmental period, but the medium size gets smaller and smaller. By the way, in standard life condition, we should observe in average a pupil size about 3 millimeters. Okay. Okay, here I show you on the left side the output, online output actually of the eye-link system, in which it's possible to online observe both eyes and the pupil here. Yeah, it's important to say that the majority, the eye-link use the information, measure the pupil diameter also in order to get information about the coordinates, the spatial coordinate of the eye. So again, it's a measure that you should find in your data. And on the right side of the screen, I show you the output of a TOBI calibration that you should be familiar with for the left and right eye. So in both system, you should be able to find out this measure. Okay. So let's move a first step into picture is taken from Method 2022. Again, I really recommend you to read it because it's quite comprehensive of many aspects of cognitive pupillometry, mainly applied to adults, but I mean, many considerations there can be also applied to infants, not all, of course, because as you know, working with infants or children is not at all the same thing, and we could not expect, for example, the same number of trial, the same repetition, or stuff like that when we work with developmental population. But many considerations there are very useful, especially about the design. So one could think like, oh yeah, I collect many eye tracking data, and so some pupil measure should be there. Oh, I give a look and analyze them and bam, bam, bam. No, it's not that simple, because pupil dilation, pupillometry needs some requirements in terms of experimental design to be properly used. Otherwise, we are just analyzing noise. And in cognitive psychology, I mean, it's not so rare to analyze noise and then conclude stuff on noise. Design. So what about the design? Stimuli should ideally be constant between conditions. This is called the Hilliard principle, and it's quite hard to achieve because if you intend to test an hypothesis, and so you have a manipulation that you want to, if you have some hypothesis on this manipulation, you maybe want to add different stimuli or different conditions. But at the same time, it's important that these different conditions are not too different in terms, for example, of luminance, color, that are quite close to the concept of luminance, and shape, because pupil also respond to shape, and a number of perceptual feature that, and knowledge, also top-down feature of the stimulus that can drive the effect. Okay, so that's why it's very important to try to take constant the stimuli and the conditions. Yeah, again, it's important to design an experiment that would not require participants to move, to shift too much their eyes, because we have seen that one of the main sources of noise and artifacts in cognitive pupillometry is also the gaze shift. So ideally, we should present stimuli at the center of the screen, or in a specific, or not just at the center of the screen, or balancing left and right presentation, for example. Yeah, trials should ideally be slow paced. That's why, for example, that's why I said that attentional blink is not an ideal construct to investigate through the lens of cognitive pupillometry, because it requires rapid presentation of stimulus, and it's better to give pupil the right time to respond and to go back to the baseline. That is not so much time. We saw that it's like around 200 milliseconds of latency after the onset of the stimulus. And so it's not like the electrodermal activity. I don't know if you are familiar with it, but it really needs a lot of time. It's a really slow measure. So you present the stimulus and you expect some second, and then it starts responding. So it's slow paced, but not so slow. Also, pupil size should ideally be measured while participants do nothing, and it can be challenging in adult studies, but in infant studies it's quite okay, because usually we do not ask infants to do anything, just watch or listen to. So that's again a good news for us, and that's why it's a good measure in infants research, because ideally, if the participants do not, because as we have seen, pupil reflects sympathetic activity. So if you have to do something, you are involving the sympathetic system, and of course, pupil will respond to this. So if you do nothing, it's better. Of course, ambient lighting should be ideally intermediate and matching the brightness of the screen. And in the March of 2022, there are many in physics. There are many definitions of brightness, luminance. It's not so easy, and we should not get crazy about it, but just consider the fact that the most we get homogeneous light in the screen and in the environment, the better is for the noise measure ratio of our pupillometry study. And finally, all data should ideally be stored in a single file per participant. And this is very important. In this tutorial, you saw that I didn't do that. I just collapsed 2 participants. I don't know if you went through the data set, but we are going to do it together. But ideally, we should store a single file per participant, and ideally, we should share data with the community, but not data that are manipulated without any, just data we collect, the single data of our participants, and sharing that also with the noise, with the NAS, with the unvalidated rows, etc. Because these lead to replicable science, unfortunately. Yeah.
Short question about the ambient lighting. How do you make sure that it's fitting? So is there some kind of measure of the ambient lighting that you can recommend maybe?
Yeah, in the paper of Matot, he is very detailed about it. For example, the brightness of the screen can be measured through the photometer. It is like a gun that you put like this, and you can record. It's a gun, like a photometer, and you can measure the difference in terms of luminance of the screen. But for each definition of brightness, luminance, etc., do exist an instrument that can measure it. So it's quite arbitrary if you decide to measure the brightness, the luminance, or whatever, or the lightness, or there are actually more than 4 or 5 different constructs that define this in physics, but it's quite arbitrary. It's okay. We cannot be perfect, but once you decide one construct, you can find an instrument to measure.
Thank you. And can you just repeat the name the paper that you just mentioned?
The paper
that you recommended something.
Yeah, in the extra resources of the OSF, there is Matot 2022. There you found all the information about it.
Thank you so much.
You're welcome. Other questions? Okay. So so far we have seen what's very important in terms of the experimental design to get the most of this measure in terms of cognitive interpretation, not just pupillometry per se. Now, hands-on data, and we go through together the pre-processing of data. That maybe is one of the most exciting aspects of doing this work, doing research in general, because you can face uncertainty, and uncertainty is beautiful. And in a way that we will see all the degrees of freedom that we actually encounter not only during pupillometry data pre-processing, but in general when we do pre-processing of any data. And I hope that you, instead of be scared of this uncertainty, because sometimes now we need to find a result, a way to do things, a gold standard pipeline, things like that maybe do not exist in real life, and instead could be more useful and informative to embrace uncertainty, be aware of this uncertainty, and be able to manipulate it and share it with the community in order to understand how a measure or a study is actually robust. So weighting the uncertainty instead of neglecting, as we usually do with p-values, for example. One measure, all information. No, it's better not to. But I hope this will emerge through the tutorial instead of just saying it. And specifically, we will see the parsing raw data, so how to manage all classical dataset in a pupillometry study, how to deal with missing data that are can be very informative, especially in infancy research. Because if you think about looking times are just a complementary measure of missing value during a visual during a classical experiment. So it is the amount of time that the infant does not pay attention to something. It is as informative, as important as the amount of time is paying attention to the stimulus. And we usually just neglect missing data and we are scared about them. But why? They are data. So again, or the importance of downsampling. In our case, it's not the case of the example that that we are going to work together, because we the data came from a Toby tracker with a sampling of 60 hours of sampling, and so it's okay. It's very good for a pupillometry study, because pupillometry with the phasic state, the response of pupillometry happens each 200 milliseconds after the onset of the critical stimulus, and with 60 hours sampling, we are just fine in capturing it. Indeed, if we use, for example, an A-link system that has higher sampling rate compared to Toby, we may need to downsampling it. Okay, even because it's very hard to manage this amount of data in terms of the weight of data and the capacity of your computer to work with it, and are not so useful, because the physiology of pupillometry do not require this higher rate. But instead, if you want to do an eye tracking study, so have precise information about the movement of the eyes, the microsaccades and stuff like that, then you need an A-link system. I would suggest. Okay, then it's important also to convert in millimeter the information of the pupil diameter changes over time, if necessary. And in our case, it's not necessary, because the Toby system and Open Sesame, that is the software I use to collect those data that we are going to work on, already give you pupil diameter in millimeters. I don't know if you are familiar with Open Sesame software. It's a free software created by Sebastian Madut. Sebastian Madut is the same guy that is maybe the major expert of pupillometry in adults. So I recommend you to go through it and use it, because it's quite flexible and free, open. So it's not marketing. It's open, it's free, and it's also.
I was just curious about downsampling.
Yeah.
That's besides the computational problem, if you have a best computer, would there be any other downsides? My understanding, I would say that we're missing data, we're averaging across changes, even if the effect requires a larger amount of time. It's in the end it adds quality to the data, right?
You say it adds quality, but do it adds a quality in a pupillometry study? I mean, you should have a constant value for. You don't have any real problem, but it's not adding value in a way that likely you will end up with a data set with a lot of raw data. It's the same value,
Yeah, of course.
So, I mean, okay, if you are running both a pupillometric and a tracking study, I definitely suggest you to have this high sampling rate, because then you can match pupil diameter changes to find spatial coordinates, and then, for example, correct for gaze shift. So yeah, but if you have a simple study in which you present a stimulus at the center of the screen with luminance constant, blah, 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 then to me, it do not add actually. It just adds you a step in the preprocessing case. But yeah, it's not, do not introduce brief.
May I help something?
Yeah.
To the answer. The fact is that you don't average. You look at the time course. So the pupil system is not so fast. So you will have just a timeline which has more intervals. Rather, maybe you will just see what happened in the time window that you are interested in. So you don't need to see.
Is if you average across windows, the change can happen at different points. So if it's the same concept with the eye tracker, even if the minimum time is 16 seconds or something, if you have a higher rate, it allows you to have this change in any moment.
Yeah.
So that supposedly, even if it's very minor, but supposedly it increases a bit the quality of the data. And when the eye tracker fails for a second, it retakes it, the amount of time that the missing values become lower because the system is faster.
Yeah, yeah.
I mean, it's very minor things, but
yeah, you're right.
I think it's probably equivalent.
Maybe if you do like interpolation, then it would be useful. Because you need more values to get through the yeah, the point is that you don't need to buy expensive eye trackers. Yeah, so that's the message. But yes, of course, if you already have, why not? It's okay, no problem.
Oh yeah, I totally agree with you. It's depends. Let's say it depends on the aim of the study and the design and the population you are using. But if you are working with infants with just presenting central stimuli, you don't need all this expensive system. Yeah, that was the. Yeah, thank you. So then baseline correction is fundamental in any psychophysiology, many of the psychophysiology measures, but it's not always required because it actually depends on the statistical approach we're going to use it. For example, I hope to have enough time to go through the script and arrive to the statistical modeling of pupil dilation. I'm recently fell in love with generalized additive mixed effect models, GAMS, and that were very, very, very nice if you like to the functional analysis or sort of functional analysis and looked at dynamics of dynamics of some of pupillometry, for example. They're very, very nice models, and in that case you don't need to do any baseline correction because the statistical model allow you to specify all the random effects in terms of trials and subjects. So I mean the effect nested by trials and by subjects, so you don't really need to do any baseline correction. But if you are going to run classical analysis like ANOVA or linear mixed effect models or whatever, maybe you need to correct data for some you need to do some baseline correction both at the trial level and at the subject level, not just at the subject level or at the experiment level, but each trial by trial. Okay, and we will see it together in R. Also it's fundamental to visualize data. Sometimes, I mean, in the old ages, people collect data, do averages, and then statistical analysis. And maybe if they they are not able to recognize, for example, the distribution of reaction times just looking at the shape of a distribution because they just expect a number, the mean and the standard deviation. That's not nice if you want to get uninformed, that if you want to capitalize on the information of you are collecting. I mean, it's so effortful to collect data, especially in infancy research, and why we should reduce all the information, all this effort just to a number, to an average. No, don't. We can really exploit and get a lot of information just by visualizing data in many ways, plotting data, the shape of the distribution, or with violin plots or whatever. Or, for example, also can be very useful to plot pupil dilation measure as a function of spatial coordination, to see the impact of gaze shifting on our data, for example. So visualizing data is half of the story, if you want to be certain about our conclusion. And then trial exclusion based on baseline, because I mean, we have seen that if we are interested in cognitive effect, we should expect the effect to be small. So if at the trial level or subject level, we found some artifacts in terms of the outliers, in terms of the great effect, too large effect, can be useful to exclude those trials. But not just excluding it. It could be useful to run the analysis with and without those trials to see how robust are the results, or how these results are driven by the exclusion or inclusion of those critical trials. This approach is called a multiverse approach. So we are not just interested in one universe of analysis in one pipeline, but we are admitting possible universe. We are in a multiverse. And so weighting the robustness of our results independently of the arbitrariness of our pipeline preprocessing choices. Yeah. And also participants exclusion based on the same logic, because maybe we could have some infants that just do 2 trials, 3 trials out of 10 or whatever. And yes, from a pure statistical point of view, maybe better to exclude them. But because it's so informative, it's so hard sometimes to get information, to get data from infants, we can include this other path in our multiverse approach of pipeline of preprocessing data. And then statistics, yeah. Statistics that is derives from the design. I mean, when you design an experiment, you already are thinking about the statistics, the number of trials. If you want to see the impact of pupillometry across with time, maybe you are thinking about some functional analysis, no? So statistics is not a room far away from the design room. It's very close to it. And it's important to take it simple, okay, because already we have included a lot of degrees of freedom, so noise in our pupillometry analysis. So it's better to keep it simple, keep single test, not multiple comparison. If you have a mixed effects approach, you don't need it. So I suggest you or also a Bayesian approach, you don't need multiple comparison. So decide in advance, of course, which windows are you interested in analyzing. And that doesn't mean being too rigid. One can change ideas or can explore. Exploration is admitted in science. The important stuff is just to say it and declare it. Oh, now I decide before to investigate this window because I designed the experiment in order to expect something in this window. By the way, now I'm thinking something else. I'm interested in investigating other aspects, and I'm going to explore. So let's separate the confirmation exploration part, and it's fine. There's no problem in this. Or the cluster-based permutation can be another nice approach, or the cross-validation. Yeah, but So far, I would like to, if we have time before the coffee break, to go through the hands-on. So, and before starting, you need to know the design of data we found in the Open Science repository.
Maybe we would also ask if are there any questions about this first part?
Yeah.
No?
Yeah, it was rich, you're right.
Considerations or other approaches could be informative. It's a workshop. So
otherwise we can move to the practical part. By the way, all the stuff I said about the pre-processing step, we are going to see together in the exercise. So if there are doubts, maybe we'll be. Yeah.
About the multiverse approach.
Yeah.
We will see it after a bit.
Yeah, in the exercise. Yeah. Once I met this approach, I cannot do anything. I mean, how can you just decide one street when you have the possibility to investigate the impact of multiple choices? Once you meet the multiverse approach, I think you cannot go back. So yeah, so we will see it. Okay, so hands-on pupillometry. Let's face the degrees of freedom in data preprocessing. The design is a very simple one, comes from the very first study of my PhD, very first one, and it's just the first part of this experiment. The first part, as usually happens, is familiarization, and this familiarization has two blocks: a visual block and audiovisual block. Both participants, all participants were exposed to both blocks. In the visual blocks, I presented a stimulus, unusual object from the noun database. I don't know if you, in the extra resources, I left TXT file with some resources about databases of stimuli, open, and so can be useful. Also, that are balanced for luminance or color. In this case, for example, I select this stimuli, this database, the noun database, because the stimuli were rated by others in terms of nameability and colorfulness. So from a subjective perception, subjective point of view, so how you think this object is colorful, because you know that also top-down effect can impact it within the emitter. And then, of course, I equalize from the stimuli, so the luminance of the stimuli, thanks to a photometer. Information get through a photometer. Yeah, so in the visual block, I presented a stimulus at the center of the screen, and it stayed there for 1 second. This is the time. And I presented for 9 times. Very boring. In the audiovisual block, so all infants, so both blocks, and of course I counterbalance the stimuli between participants and between blocks. In the audiovisual block, I show an object from the same database there, and after 100 milliseconds, a sound appears. And it is expected to be the name of this unusual object, COBA. Also, the noun database offer you some novel labels. So you can get both the visual stimuli and the labels that are controlled for a number of variables in terms of cross-linguistics aspects, stuff like that. I'm Italian. The infants I was going to test were Italian, so I selected, for example, COBA, that is a classical lexical form of many words in Italian. So consonant vowel with the strong accent at in the first syllable, COBA. Cool. It's actually COBA. Okay. So this is the design. Okay. Very simple familiarization. Again, also the audiovisual block was presented 9 times, so very boring. The order was counterbalanced. of course. And yeah. So now we are going to see the data set. So we will see together the data set, how to read it, and then we will explore a portion of the multiverse through R in the preprocessing of the pupillometry or of the pupil data. I said a portion because it's impossible to investigate all the possible paths that a preprocessing can lead to, right? Possibly there are many aspects that you can vary, but it's already important, at least important to investigate a portion in order to get information about the robustness of your data. So,
can I ask just one question about the design? So each child saw 2 objects, 9 times, one was labeled, one was not.
Exactly.
And that's all.
That's all.
Okay.
Thank you. It was much easier like that. Yeah. Yeah. In a counterbalance order. And yeah. Okay. So I ask you to go to the Open Science.
Yeah, in the meanwhile, this is the part of the experiment that we are going to see today. The words I was speaking.
Yeah.
This was the familiarization phase.
I was just wondering whether they were much more objects that the children saw. Or...
And I guess now the data is stored in one file.
Yeah.
Was there like a step in between where you kind of merged it, or?
No, I start with a TSV file. I just converted in TSV to make the tutorial easier. Yeah. But at the very beginning, it was a TSV file identical to the one I'm showing you, and separated for each participant. Because with Open Sesame, you can talk with Toby. Open Sesame is the software I used, open software, and you can talk with the Toby and ask him to write the column you need about the design directly in the TSV file, and it's quite, I mean, would be a best practice. I mean, because you don't have to merge. I mean, each time you merge, you don't know what maybe you are going to introduce some problem, some error, you know, and so if you can avoid to merge, it's better. Okay, so I ask you to download the dataset. Let's go through it together a bit. So again, as I said before, this comes from Open Sesame and Toby system. So it's quite specific to this setup. But at the same time, the main information we can find here should be there independent from the system you use, because those information are necessary to. So we have the timestamp that is, as you know, the time clock of the computer, nothing else. The gaze point X and Y, sorry, left and X and Y of the left eye. So the coordinate X and Y of the left eye. We have an indication of the validity of the measurement, validity left of the left eye, that tell us basically whether the specific measurement was correct, was okay, so the tracker was able to collect data. And the same happens, we have the same for the right eye. As you can see here, there are this number reflects the actual coordinate of the screen in pixel. Okay, this number here, for example, gaze point X left correspond actually to the pixel of the horizontal axis of the screen. And you can see that there are -1. -1 in this case indicates that the validity the tracker was not able to collect a good measurement. It could depend on the fact that eye tracker for any reason stopped work, or more likely that the infants just looked away, as you know. And as you can see in the validity column, we have 0 that indicated it was not valid. So we have double check that the measurement was not good. And I shared with you all these raw data, they are called raw, let's be raw. Do not, when you share data with the community, leave it there, because they are data. They are talking about behavior of infant. Don't neglect it or be ashamed of all these. Oh my God, I have a lot of missing data. That's not good. You don't know. Can be useful for further investigation to know, for example, the amount of missing data. Because sometimes some reviewers say to me, but you have too much missing data. How can you say that if you don't have any information about missing data in infant study? Okay, and it was like, you should remove it, because it's not elegant to see all this missing data. It's not elegant, but it's actual data. They are data. And the fact that usually we are not keen to share missing data doesn't mean that we don't have it. So don't be shy. And in this sense, again, and let's embrace uncertainty. Let's embrace why we should be scared about it. And nice. Again, okay, let's move on. So we also have the pupil size left in millimeters. Each 16 milliseconds, because we are talking about 60 Hz sample rating. So each 16 milliseconds. And you can also give a very rapid look and see if you have any strange values, and extreme values, because as we've seen before, we expect we know the distribution of values, extreme values, which should be.
We have to check also about the dot versus any change in the measure between the pupil size left and pupil size right. Sometimes, I don't know why, but when you import data on Earth, maybe some columns can change. So you must check that they have the same
decimal sign, because in R you can you use the dot instead to sign the decimal value. Okay, and you have the pupil validity of the pupil size validity of the left eye and of the right eye. And then you have the condition, that is familiarization. And familiarization. The familiarization type that is here is called labeled and unlabeled. Stand for visual and audiovisual, and as we've seen before, the session, so the trials 1 to 9 for each block. The AD, that of course that is basically the number associated to each participant. The average between pupil size left and right for each row, and the time locked. Okay, the time in milliseconds locked to the start of each session. Okay? Nice. Question about it? Yeah.
Would you always recommend averaging across left and right and just pick one eye, for example?
Yeah, I recommend to first to plot the correlation between the pupil size, both eyes. Yeah. Plot it, not run a correlation, but plot a scatter plot of left pupil size, right pupil size. But we are going to see it, to plot it in R and see if actually they correlate. not just a number that is the average, blah, 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 I don't know what, but see how many data points do actually correlate. Yeah, I will recommend it. But then we are going to use the average because if we expect we expect a high correlation in the order of 0.8, 0.9. It's big for psychology stuff. It is not psychology, it's physiology, and then we can average because with a 0.9 correlation, we are quite confident.
Also because if you, for instance, if you in the room where you're testing, maybe you could have like a light on your left, so the value of your left pupil could be like a bit smaller or bigger than the right, not because the pupil are actually different. This is not supposed to happen, but because the Toby or die link is like a bit confused about the light reflex that the measure based on which it calculates the diameter. So,
perfect. Okay, so yeah.
I have just a question about the validity variable. Does it, when it's valid, does it mean that just the pupil has been detected, or is there another criterion to validate?
No, exactly as you said, just means that the measurement was correct. So the eye tracker was able to collect both the coordinates, spatial coordinate in the both axes, and the pupil diameter of that eye.
Okay.
Yeah, just this. So for example, if you have a strange value like, I don't know, 100 millimeter, you cannot find any information in the validity column. It will be, it's okay. It's, I got some number, but then it's, yeah. Thank you. Other question? Okay, let's open R and then we will have a short coffee break. Yeah.
Sorry, just regarding this decision about the two eyes and I was thinking if the calibration measures, because I'm used, I never analyze pupils, but for the position, I'm used to just taking the calibration and the lowest value of calibration to choose the better eye. And I was wondering if you use the calibration in any ways for having, I don't know, some threshold value that you accept or not. It affects a lot of the pupil measure or not.
That's nice suggestion. That's cool. No, I usually do it post hoc in the statistical part, in the statistical model, by specifying a smoother term that weights the impact of the spatial coordination x and y, x and y on the pupil diameter. So it's something like that, in a way that you can associate the error or the variance of the diameter as a function of a specific spatial coordination that is not just let's say locked to the points you calibrated, but is on the wall coordinates that the eyes went through. But I usually do it post hoc.
You confirm for position, but this doesn't have anything to do with calibration.
Yeah, of course, calibration is a step that should be, it's a requirement. So we always check for a good calibration, otherwise all the information can be rubbish. So yeah, the calibration step is fundamental, but I do not, but it's a nice suggestion. I'll try to use it as a prerequisite to include data or not. Can be nice suggestion.
I think even like probably if you use, I don't know what data, how raw the data is that you take, but Toby and iLink, they have software that they do it already.
Okay.
So there's some filter. Maybe if you take it with this software, you're saying it's raw and there's no preprocessing. I don't know. But if you use the main Toby things, they already say missing value or give you problems or something. So they have their own threshold.
Yeah.
My question was if these thresholds change for checking for position or pupil.
No. Okay. Oh, sorry. So I misinterpreted your question. No, no, because eye tracker are mainly built for eye tracking studies, not pupillometry studies. As I said before, and Matot also say that in the 2022 paper, eye tracker are not the best instrument to do pupillometry. So yeah, the threshold that you are talking about in terms of the goodness of the calibration is just based on spatial coordinated spatial measures. Yeah. Okay. So if you want to, if you already downloaded this data set and you open the script, the R script. Okay. I'll try to. Okay, should be something like that. Okay, so maybe I'll be a bit boring for those of you that are already users. Sorry, but we go through all the lines for those people that do not are familiar with R. So first of all, we remove everything from the environment, so we can start from with a fresh start with no previous information, and then set the working directory in which we are going to take the data sets and work on data and stuff like that. So I don't know which is your you can see it clearly, or maybe it's better to, no. So yeah, and then so you set your working directory, and then you in this case with the function read.csv, you can upload the dataset. Yeah, everybody's there.
If you have trouble, just raise your hand and I will try to help you. It's okay. A nice check before starting any pre-processing is to give a look at how data are stored in R. This can be meant as a data parsing part of the pre-processing. It's very important because it's a prerequisite to then have the right conclusion based on our analysis. So what I mean with that for example, gaze point x left, this column is expected to be numeric, yeah, because it contains the coordinate in pixel of the left eye on the horizontal axis of the screen. So we expect to be a numeric one. So what does it mean in R? That when we have the summary of the dataset, we should have all the statistics, descriptive statistics that can be applied to numbers. So minimum, maximum, median, mean, and no. So we are sure that here R is reading the variable as we expected yes to. So I say he, but maybe it's a she. I don't know. And the same for gaze point left, for validity left, and so on and so forth. We expect all this column to be numeric, right? And it's important to check it because otherwise then when we do stuff and data management and data parsing and blah, 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 maybe we can encounter a problem and we don't know why. And it's simply because we did not look at the summary at how R is reading the identity of each variable. So it's a fundamental step. Can be boring, but it's very important. It's a sanity check, let's say, of the pre-processing start. Then we have condition. Condition, in this case,
we have only familiarization, but as I said before, in this experiment, there was another step that was a test phase, as usually in advanced research, not so original. In this case, we do not expect this variable to be a number. We do not, because we expect condition to be a string of character, familiarization, right? So here tell us that we have this number of rows with this label, familiarization, within the column condition. Again, session is a number here. Then can be changed to, for example, a factor if we need to use it as a factor for some reason. But so now it's okay for us if we have this session variable as a number. And nicely, we can check if actually there are 9 trials, 9 sessions as expected as. So it's also a sanity check in terms of how the experiment has been implemented. Sometimes happens that we have number of trials that do not match what we expect or we design, no? And so it's a good way, rapid way to have a sanity check of the design. Then the familiarization type again is a factor, so I expected R to read it as a factor, and indeed he does it. So we have more or less the same number of rows for labeled and unlabeled familiarization type, not the same number because infants are not adults. So if we ask them to do the number of trial for each condition, they are not going to follow what we want, no? And they know. So, but more or less, we have the same amount of raw data for both conditions. We have the ED column that now is treated as a number, but we don't want it to be a number because it's also a factor, right? So we are going to force R to read this column as a number, as a factor. So we can nest it all the measurements as a function nesting of the identity of the participants. Then we have average and time that are treated as numeric, and it's okay, it's what we expect. So yeah, I write. So the data set has been read by R in a nice way, so it's okay. But I put here the how to parse and how to force R to read a variable in a way so you can use it in case R does not read a numeric variable as you want. And it's important here to notice that it's fundamental in R when you want to modify a variable in numeric, first to modify it in a character. Yeah.
It's not always the case. When you implement data, it's always considered like a class character.
Sorry?
When you implement data average or by default, it's always as character.
Yeah. Yeah, it's not always as character. It can be treated as numeric or as integer or as character or as factor in as many. And yeah. Sorry?
For me, it's always okay when I implement data.
Okay, you're lucky. No, you're like, no, it's not always like that. Sometimes it is, for example, read a numeric column as character, and then you cannot do operation as numeric because is a character, and so you have to parse it. Or, for example, if you just write as numeric without as character, if you have, I don't know, if R read a numeric column as a factor, let's say, and you want to say, no, I want that you read it as numeric, and you just put numeric without as character, likely R will introduce some error in the numbers. It happens. So that's why first you force it to be a character, so in a way it prints the exact sequence of number, and then he converted it to a number. So that's why I put it here, because it's a very common error that can happen. Yeah. Also could be useful. For example, I recently worked in a multi-analysis, multi-laboratory project, and also the data set came from different countries. So sometimes, labels can change depending on the language and can be quite like that. And so it can be useful in R to modify the labels in order to have homogeneous labels and not, for example, mixed Italian, French, British, and whatever. And so in line 14, in line 14, you see the how to modify the labels in order to get all the labels in this. For example, in the data set here, you said labeled and unlabeled. But before, when I show you the design, I talked about audiovisual and visual, right? And it happens. I don't know. It happens to me. I don't know if it happens also to you. That sometimes we write a name and then another name and a synonym, etc. In this way, you can easily make all the labels just the same, and yeah. So all these steps are just data management, and I hope will be useful for some of you. And finally, before the coffee break, also can be useful to set the window here, the time window. If we, for example, say I want just to get the data set in this time window at the trial level. So I say the data set is called data. In the column time, I want all the values equal minus a certain value time. Okay, so yeah.
I think it's kind of reassuring that apparently in your data you also have time values that exceed the actual value of the duration of the trial, which happens quite often, I think, in TOBI, which for me is quite unsettling, because I think, well, this should be quite accurate in terms of timing with the side tracker. But what do you think about that? Is it just fair to just chop off the rest of the trial and just use the first?
I do it on R. I share. Yeah, I totally agree with you. It's really a pain. Yeah, I usually share all the raw data and then the script, so it's clear what I'm doing. And in my case, I think that this problem is due to the contingent procedure. So each trial, the next trial starts only if the actual looking time is up to something. So if for example, the infants look away, the eye tracker is collecting data that will be missing values, because we still have missing values here, for example. And so the timing of the trial will not match what expected, just because it's contingent procedure. I don't know if I can explain this.
But we don't have contingent procedures. The trial is 14 seconds, but sometimes it's 14.2 or so in TOBI, and
yeah.
How strange.
Yeah.
For instance, like a reviewer of mine, from inside, he just suggested that it could be like a delay in the log phase of open season for us, but maybe it could be also delaying the transfer of the data. So it's not actual data, but like time of delay could be also like this. But yeah, it's very common actually.
Yeah. But I don't know if some of you use iLink, or you found this problem also with the iLink system, or it's just a topic.
I don't remember the iLink. I think it's more accurate, but with the TOBI, it's very common.
Yeah.
And it's always the question whether you cut off the end or the beginning. Because if you say there's a delay at the beginning to show the stimulus, then you should corridor there, but I don't know. I was just wondering that.
Yeah.
Sorry,
yeah, it can also be that Toby is not. I mean, it's not so accurate at many levels. It's flexible, so I mean, yeah. But it's it happens. Yeah.
But a way to handle these things, which is also useful for pupillometry, cognitive pupillometry, is to leave like 1 second of silence after the experimental trial. You leave just 1 second, also to see the change in the pupillometry, to see whether it comes back to the baseline or not, wherever. So you can like see what happened also after at the end of the trial. And the same way you leave like 500 milliseconds of no simulation at the beginning. So you are sure that the range of values that you're interested in are present in the trial, and then you cut off the rest, or you use it for the baseline.
Yeah, by the way, it's a mystery.
Yeah.
It's also called what you said, that always visualize your data to see what's going on, because the values, you need to see it in order to interpret.
Yeah, in a way, errors are the only certainty. No. Yeah.
And so why do we cut the time? Why do we don't take this milliseconds after 1000?
Because from a theoretical point of view, the time window I'm interested in is the first second, let's say, but it's completely arbitrary, and you don't apply this filter. It's, let's say, a degree of freedom I'm introducing here to answer a specific question I want to answer. But yeah, it's not a requirement. It's just to align all the time windows in my view and see what happens in the first second I show you something, let's say. But it's completely arbitrary, and it serves to answer a specific question. So you can leave this filter open.
Okay, so we are sure that in 1000 we have what we want to see, and we don't need the rest.
In this pre-processing, but then the raw data are there. I'm not modifying the dataset. The dataset stays there. I'm just virtually modifying the dataset. So if in a second time, I say, well, let's see all the independently from the time window. Let's see what happens if I include all the time values. I can do it in another script, for example, and yeah, it's okay. It's just arbitrary, and it's just a way also in this tutorial to show you how to filter by time, because given that pupillometry, as we have seen, can be interpreted as an event-related measure. Maybe you can be interested in just take a picture of a specific moment, and with this filter, very basic filter, you can decide which time window you're interested in. It's just a matter of an exercise, but yeah, good question. Okay, guys, let's have a coffee break, because yeah, and see you at 10:30. So with the coffee, everything is better and clear. Okay, so I'll be a bit faster moving into the script, and I know that could be a problem for some of you that are not really familiar with R, but no worries. You can just raise your hand, and Sophia will come to you and eventually help you understand some stuff, because I'm aware that for those of you that are not familiar with R, maybe this script make not so sense in a way. That maybe is not clear, for example, what an object is in R, how you can call a dataset, or what is a function, or even the syntax can be not so clear. But it's okay, because if you're not a user, I mean, it's completely understandable. So don't worry. Raise up your hand, and Sophia will come. And also, in the OSF repository, you found some in a TXT file called tutorials, something like that. in which I suggest you some tutorials to begin with R, which are very nice. I start with that during my PhD, and I found it very useful. And so don't be scared about the syntax of R. It's like a language, so once you are more familiar with it, it will be very, very straightforward. And also, the nice thing of R is that the R community is really open. It's easy to find suggestion on Google, just Googling it. I especially suggest you Stack Overflow, site Stack Overflow, in which there are many topics and discussion about many problems and errors. Also, the nice thing is that I always talk with you and say exactly which is the problem, if you are a problem or an error. So it's quite, it's clear. So also, I see I used several packages that has nice function to proceed with data management and make life easier compared to Excel. So so it's save your time and makes things working just fine. So we were here. So we applied the filter, the time filter, that is not, as we said, required, but in this case, just for the tutorial, is there. So we limit our timeline to 1 second. And now the next step is replacing the missing data, then -1 that we found in a data set, with NAS. Okay, thanks to this nice 5 and this nice function replaced with NAS. Clear? These allow us to do not manipulate the structure of our dataset. So we will left the NAS. Without this NAS impact our computation of number. Instead, if we left -1, it could introduce some mathematical problems because it's a number, right? So by doing this, we replace this line, we replace a -1 with NAS. But actually, before doing this, I would love to show you what we said before. So visualizing data is fundamental to understand the quality of our data collection. How many missing data. Also the quality of our data collection in terms of which values of part of the pupil we have actually collect. So I usually love to plot it like that by using the dplyr package and also the digipub package. Error. Yeah, because so here, answering the question before about to check whether we are actually legitimate to average the pupil diameter, the best things to do is just to plot the pupil size of the right eye in millimeters, of course, and the pupil size of the left eye in this scattered plot, in which I specify to color in gray those values that may be extreme values. Okay, we have seen that pupil diameter can vary from 1 to 9, but this extreme value may be the result of some artifact of some gaze shifting or whatever. So it's nice to see the amount of these extreme values together with how did both eyes correlate. This ensures us that we are actually a good measure, physiological measure, because we expect both the eyes to correlate a lot. And as you can see here, the correlation is close to perfect. In black, you have the pupil diameter, yeah?
This is not in the code, right?
This is not in the code, no, yeah, but I will upload also this,
No,
sorry.
I was just like thinking that maybe.
Yeah, I work on it because after the question, I
Oh,
was
yeah,
like,
yeah.
I should show it. And then during the course I did. But of course I will include it. And I will upload another script with all this picture, no worries. Okay, so I think it's very useful because it's a picture of the actually data collection quality. Yeah, and it's nothing spatial, nothing incredible. No, it's very expected, but can be sometimes that we have, for example, here we have not many nulls, actually no nulls, no, not -1, right? And so we are quite confident that these data are collected nicely. But here we encounter our first degree of freedom. That is, are we allowed to include all those data in our final statistical analysis, or maybe could be better to just reduce the range of values between 3 and 5, as many authors suggest too. Okay. Also, yeah.
What if you have a really obvious outlier in there? Would you make a decision to exclude the points? Because for now, I mean, you were talking about the 3 to 5, and it really looks like a cluster, but if you have outliers, what would you do?
Yeah, good question. In a classical approach, usually you just neglect it, remove it, and proceed with your pipeline of product preprocessing analysis without considering those extreme values. But again, having in mind a multiverse approach can be very interesting to run two. This is the first working path that we encounter, and see. So we start with one data set, and now with this working path, we have two data sets. One that includes all values, and one that includes all the best, let's say, the most plausible or more, I don't know, values. And ideally, and that's what we are going to do, we will run all the analysis on both datasets to see whether our results are robust enough independently of our arbitrary choice to include them or exclude them.
But is it really that arbitrary? Because do you have a good hypothesis for why those my eyes would be so different? It seems like anyway it would be a bit rubbish.
Yeah, you're right. Yeah, because as Sophia said before, could be that something in the environmental setting could lead one eye to be, I don't know, more dilated than another for any reason.
Sometimes, I don't know, one eye is watery or something, and they use one eye, and then I would, for example, exclude the one that is super out of the count.
Yeah, you can do that, but you will never know if you just exclude it. You will never know if it has an impact on your results or no, because if let's imagine that including this extreme value does not affect your result. Including it means increasing the statistical power because you have more observations. Or if it actually modify your results, then you are quite confident it is an influencer case, an outlier. And then you are more confident, in excluding it, for example. You are not modifying the dataset, okay? You are just getting you are just getting more information about the robustness of your data. Because even imagine that one eye, is more dilated because the source of light is on the left, and so the right eye is more dilated because ants want to get more light compared to the left eye. But the dilation, okay, because we are interested in the relative dilation compared to a baseline, is the same amount, let's say, okay? So it's not an outlier, indeed, because it's talking about the same effect. Was I clear?
Thank you. Yeah. The same thing could be said, like if you work with babies, like very young, like 2 or 3 months, maybe they are like this, they are not like this. And also the distance between the face and the tracker can influence the diameter. but then you can move. So you have like just a complete different value. So it strongly depends, I think, on the eye tracker that you use. Because for instance, when you use a link, you can see the pupil of one eye, so you may be cautious about what is going on. But for instance, with Toby, you can just see on one of the two eyes alone. So it's up to you. But
yeah, it's up to you. But the nice thing is that if you consider it and visualize it, is already up. You are adding information on the quality of your experiment. Then it's completely okay if you decide to exclude it. But the point is, sometimes we do not do this work before that analysis, and then it's just this. It's just to let's say increase awareness about how important it is to visualize data. But then the decision is on you.
Sorry, can I ask a quick question about Toby and the validity? In that version, so if one pupil is detected and not the other, is Toby sensitive to that? So the validity would be a 1 for one eye and a 0 for the other?
Exactly, yeah. Okay. And then, nice question. And then you are facing another forking path, another degree of freedom. And for example, you can decide of interpolate one eye, the missing value of one eye based on the other eye, because overall, for example, you find that the eyes highly correlate. So you are entitled to input the value of that missing, or exclude both eyes, or treat just one eye as an average, a plausible average. These are all arbitrary decisions that can affect your statistics. They can actually affect your statistical results. So, given that are good choices, all the three choices are good choices. Also, excluding that rows of both eyes could be a good. It's actually included as a good choice, but you don't know, for example, how this degree of freedom can impact. So a multiverse approach allows you to see whether is the pre-processing choices that lead to the results, or if the results are there independently of your. So yeah, but by the way, yeah.
But also this is the main point of disentangle between missing data and invalid data. But they are not the same thing. You should include missing data because they're important from a behavioral perspective if you want, but you should not include invalid data because physiologically you can have like 1 millimeter pupil. I mean, could be, but you can lie.
Yeah. Another degrees of freedom that we should consider during our preprocessing pipeline is related to the spatial position of our data measurement. In this plot, I plot you the pixel, the gaze point left, the y of the y-axis and the horizontal axis of the screen. So let's say this is the whole screen, okay? As you can see, even if you don't know where the area of interest was, you can infer it, right? Here there was something, right? And this is another sanity check. Even if you set the area of interest before, as usually we do with eye tracking studies, then we cannot be sure that the infants actually looked at what we think is the main attraction point. So it is a very good, in my view, a very good sanity check to actually see if the areas that we expected to trigger the attention of infants actually trigger it. So in this case, for example, with the majority of our data, we are considering 2 subjects here, okay, and 9 trials per subject, not 18 trials per subject, because each infant was exposed to 9 trials in 2 familiarization blocks. So these are just the data of 2 infants. In this case, the majority of data collected were actually where we expected to be. But as you can see, there are some data that are outside the area of interest. What we do with this data? Because we know that the measurement of the pupil diameter depends on where the gaze is looking, where the gaze is looking at, no? So the position, the spatial position has an impact on the pupil diameter. Again, we can decide to just exclude them, right? Because may introduce an artifact, or open another forking path and see whether those data influence our statistical results. One could say, but why you do that? No, I mean, it's likely those data points mislead the results. But guys, we work with infants, and data are, excluding data is also an ethical aspect, because it's effortful and time-consuming and expensive to collect data with infants. And so when we decide to just exclude data, we are doing a very hard decision. So instead of just excluding that, my suggestion is open another forking path, in this case, and see whether including or excluding those data points to have an impact of your statistical analysis. Yeah.
Just quickly ask, so presumably you'd also want to check the calibration, right? Because calibration is going to influence the positioning on the screen. And you might come on to this, but I'd just be interested in whether you'd look at this in relation to the quality of the calibration as one of the checks on why you might have.
Yeah, as I said before, usually there is a threshold, as we said before, there is a threshold at the very beginning of the experiment. So if you do not meet the basic requirement of a good calibration, you cannot proceed with any data processing, because simply you don't have enough accuracy to link the pupil diameter with anything. Especially if we are working with cognitive pupillometry. If we are working with just pupillometry and you are interested in luminance of stuff, can be okay. But it's a prerequisite. It's the first requirement that should be met. Okay, another way to look at this information. So the amount of data collected within or another part of your screen, within the area of interest or outside your area of interest, is visualizing, for example, the density plot of your data. And it's also not very more straightforward, it's more clear. We have the gaze point, for example, of the Y. Let's see of the horizontal axis, and here it's clear, no? The majority of data fall exactly in one area, and so we are quite confident that our experimental work, in the sense that we expect infants to pay attention to a specific area, and indeed data postdoc says that. So even if we did not select any area of interest at the beginning of the study, we could do it as a sanity check and as a postdoc, let's say. Okay? So. Okay. So, it can be that in our dataset, even if we replace our -1 unvalid rows with nulls, we can still have some incomplete cases, so empty rows. So with this function, we can alternatively eliminate all the rows that do not contain numbers. Is that okay? Okay, and see with how many row data we end up with this. It's important to take to take track of this information, because this information is also let's say, a metadata that give us tell us about the quality of our data collection. Now we start with a number of rows, and then after some steps, we end up with how many rows. Ideally, we should not lose too many rows, no? In order to be quite confident in our data collection. Okay, so now we can actually start our pipeline, our preprocessing pipeline, encountering our first degree of freedom. That in this case, and this is completely arbitrary, we decide to put the encounter the first forking path that is dealing with extreme values. So we started with a data set, and now we are moving to have two different data sets. So the first data set, I decided to call it all, okay, and actually is the same data set that we have worked so far with. And also I add a column that I call step, because it's the first step in this multiverse, in which that I call implausible. Okay, implausible because they include extreme values. Okay, then I create a second, data set that I call plausible. Okay, so we have all and plausible now. We have two data sets. Starting from the data set data, we are ending up with two data sets in which I filter only those values included in a smaller range with the minimum 3 and maximum 5 millimeters in terms of average diameter. Okay. Also in this dataset, I add a new column, step, the same name, and this time I will write within it plausible. In order, at the end of this trip, in order to evaluate the impact of these choices, these preprocessing choices on the final statistical results, I list the two datasets in one list that I call all plausible. That just signal that in this list we have the two datasets called all and plausible. Okay, so we start with one dataset, now we have two datasets, but we have seen that could be another working path, another degree of freedom that maybe could impact our results and our interpretation then. That is the area of interest. We have seen that some point, not the majority, a few points felt outside the area of interest. So we are going to create two other datasets. So we will end up with 4 datasets, including or excluding the data points outside the area of interest. I do it with a simple R syntax. I mean, you can do it in many ways, like in life. In R, like in life, you can do the same thing in many ways. But I think that using the simple R syntax instead of complicated library is more helps replicability, because libraries, packages are updated. Sometimes they do not work with new version of R or with some computers or blah blah. But if you use simple R syntax, you do not have this problem. So but it's just my personal choice. You can do whatever you like to filter this. So what we are going, we create another dataset called all, area of interest all, in which we filter from the all dataset those gaze points that fall within the area of interest. Okay. As a good sanity check, I suggest you always to give a look to how R is treating your variables in order to be sure not to introduce errors during this path. So the summary of the dataset is always a good idea in my view. Okay, we created the dataset AOE that has all the values, also the extreme values, but only falling within the area of interest. Then we do the same thing with a plausible dataset and filter. We create another dataset that is AOE plausible, in which we filter data points only falling within the area of interest. And again, I create a list that I decide to call AOE, but you can call it PIP or wherever you want, listing these two datasets that derives from the second degree of freedom. Okay, so we start with one dataset. Now we are dealing with 4 datasets. Can be messy, not so messy. I mean, we are increasing uncertainty. We are facing uncertainty. So yeah, there is chaos, more chaos here, but less arbitrariness. Okay. The third degree of freedom that I'm suggesting you, please notice that those degrees of freedom are plausible in my view, and not your degrees of freedom, but you can find some other degrees of freedom that are even more plausible or can affect even more your data sets. In this sense, we are exploring a portion of the multiverse. But we can come out with other degrees of freedom, and that may or may not impact our dataset, and it's okay. The third degree of freedom that I'm proposing you aims at weighting the impact of the median of the baseline correction. As indeed, we know that in cognitive pupillometry in general, but also in cognitive pupillometry applied to infancy research, there's no gold standard about the length of the baseline. It really depends on your design, and also within a design, within a same design, there is no it's not mandatory to have a strict length of baseline. Okay, there are many plausible lengths of baseline that can be implemented. For example, if you remember the design, in this case, I presented the stimuli for 1 second, but in the case of the audiovisual familiarization, there was 100 milliseconds in which the stimulus was presented silently. And only if the infants look at it, then after 100 milliseconds, then the sounds appeared. So within this window, 100 milliseconds, it's possible to select multiple lengths of the baseline. In principle, I don't know if selecting a different length can have an impact on my data, right? So usually we arbitrarily select the most plausible theoretical length, but we do know empirically, and we do empirical science, we don't know whether this choice actually has an impact. And so if the final results depends on our choice instead of the effect of interest. So I decide to select 3 possible lengths of the baseline to correct my data and see whether these 3 possible baselines have actually an impact on my results. Specifically, I decide to select the shorter length, that is 16 milliseconds, because we are dealing with 60 Hz sampling, so each 16 milliseconds the Instructor collect data. So this is the minimum, the shortest one. Then I select 100 milliseconds because, as I said before, is the time in which in both conditions the stimulus is silent. okay, in both in familiarization type. And then I decide to have, let's say, a longer baseline, 200 milliseconds, based on the fact that even if after 100 milliseconds the sounds appear, the pupil dilation has a 200 milliseconds of latency before its response. It's not time locked. I mean, there is latency, so it's plausible to think that also this baseline, this longer baseline, is plausible, can be implemented. So I specify the degrees. And notice, now we are applying this free level degree of freedom, so 3 different baseline on our 4 datasets, right? So we are going to end up with 12 datasets, starting from 1 data collection. And yeah. I do it using just, again, a simple basic R syntax for the reason I said before. And basically, I create 3 universe. The universe 1, in which we include the 4 dataset, okay, all plausible, in which it's a list, we said, in which there are 2 datasets, only plausible, and OE, in which there are 2 datasets, all OE and plausible OE, right? And I apply the first baseline, the shorter one, with 16 milliseconds. But how I do it? I do it at the subject level and the trial level. So for each trial and for each subject and for each familiarization type, I calculate a baseline of 16 milliseconds. So the first true data. And then I create a column called baseline. That is actually the difference between the average column, average row, minus the median. I mean, here the median, but it's just one number, no? Because 16 milliseconds refers to one row, minus the first value, value of each trial for each familiarization time for each subject. Okay, so I launch this. Here in this cut, I put a sanity check in which R give me the value of baseline of the first row for each subject. That is indeed 0, as expected. There was a question. Yeah.
Sorry, can you briefly explain the idea behind the decrease part?
Which one? Which line?
Yeah, 65. So you just create a vector with 1 to 6 and then 1 to 12, and this is going to represent exactly what?
It's going to represent the 3 degrees. We are going to use it after we run all the degrees.
Okay. And then this is just something you calculated before, or
No, it's just a vector, as you said.
How do you know it's 12?
I know it's 12 because I started with 4 datasets and applied 3 baseline correction to each one, so it's 12. Okay. Thank you for this. Okay, so now the first universe is there with 6 datasets, right? We proceed creating the universe 2. We basically do the same thing, but now my baseline has a length of 100 milliseconds. That is basically the first 6 more or less rows for each trial, for each participants, of each familiarization type, right? Okay. Again, I have a sanity check to see which is the resulting value of the first row of the column baseline that I expect to be 0 or close to 0. Yeah, it's how baseline works.
We talk about 6 data sets, but we don't have 4. We don't have the all plausible. Are we in?
Yeah, it was 4.
Yeah, 4. Exactly.
Because we say we use the 200 milliseconds for 6 data sets.
Yeah, sorry, no, you're right. My mistake. Yeah, because it's 8 actually, because we have 4 without baseline and 4 with baseline now. Yeah. Yeah. By the way, we will work on at the end. We will work with 12 data sets because we are applying pre-baseline on the 4 starting data sets.
Yes, but
yeah, okay. Makes sense. Yeah.
Yes, it's 4.
Yeah, it's 4.
Okay.
Yeah, it was my mistake. Yeah, sorry. Okay, finally, we applied the third plausible baseline, the longest one, that is 200 milliseconds. And we create the universe 3. Again, starting with our 4 datasets. This time, the baseline will be the difference between the average row, the column, minus the median of the first 12 rows, okay? And again, as a sanity check, we see that the first row for each participant in the baseline column is 0. This is the first sanity check that indicates that our baseline correction was correct. I mean, was done nicely. Because when we correct for the baseline, we expect to align all the trials and subjects on 0, right? Is that the main aim of any baseline correction in psychophysiology? Okay, so now let's try to visualize how this baseline may impact or distort our data, okay, to see if they actually, because we know that also as a sanity check to see whether the effect is too large than one expected in cognitive pupillometry. Again, this okay. Here we see the comparison of, you don't give me the 16 baseline. Again, this plot that I'm showing you is not present in the script, working during the pause, but I will upload it on the OSF. And basically is it takes one dataset among the 12 datasets we have built to check whether how this baseline correction distorted our data as a function of the length of the baseline, right? So, okay, here I forgot to put the 16, but it's okay. Actually, this is not, sorry, coming. Okay. Let's see this. Oh. Okay, as you see here, it is written on baseline, but actually is the 16 millisecond baseline, and it's easy to notice because it's it starts from 0. So as you can see, the baseline length actually seems to have an impact on our data. What do you think? But in terms of dilation, of the amplitude of the dilation, but it seems not to have affected the direction of the effect. In the sense that the audiovisual familiarization emerged to increase, to boost pupil dilation across time, compared to visual familiarization independently from the baseline correction. Right? Do you agree with me, please? So we reach one first information. The selection of the length of the baseline does have an impact on our data. Yeah, it is. Especially if we are interested in weighting, in estimating the actual effect size, right? But did not impact the direction of the effect, because we are interested both in the effect size, how much an effect is there, how big is the effect, but also the direction of the effect. So here seems that the selection of different lengths of a baseline do impact the effect size, but not the direction. And I would like to remember here that we are looking at just two infants, okay, two participants, and just 9 trials, 4 participants. And we have, already, without any statistical inference, we just have a sense of the robustness of the effect, don't you? We include several degrees of freedom, but an effect of higher pupil dilation predicted by the audiovisual presentation seems to be there. Yeah, sure. My degrees of freedom, my forking path have an impact on the effect, but not on the overall conclusion of these results so far. Okay. By the way, we usually need also some statistical suggestions or statistical evidence that the effect is there from a statistical point of view. So, as I said before, it's important to evaluate how all the degrees of freedom that we encountered do have an impact on the statistical inference. And so we are going to see it now. By means of those models that I said at the beginning I'm in love with, that are the generalized additive mixed effect models. The generalized additive mixed effect models has many qualities. The first one is that they generalize to different distribution residual families. You know that ANOVAs, t-tests, and linear mixed models forced a distribution to be normal. Expect a distribution to be normal. But in the majority of cases, the distribution of our data are not normal. Because in order to be normal distributed, we should have a 0 as a mean, and the distribution should go to 0, close to 0, on the left, on the right, right? This is a perfect Gaussian. In psychology, basically, there are no normal distribution, okay? And we always use ANOVAs and students. I don't know why, but it's what we do. We do since ever. So this is the first quality of generalized additive mixed effect models. They generalize to different families distribution. So the estimation are simply more plausible because they respect the nature of the residual distribution. Then they are additive, not linear. When we use ANOVA, t-student, or linear mixed effect models, we force the relation between, for example, pupil diameter and time to be linear. But looking just at the descriptive measure, we are not running any statistical stuff here. We are just plotting data across with time. We see that there's no linear relation, and we should not expect the relation between pupil diameter changes and time to be linear. But if we use an ANOVA, if we use a t-student, and if we use linear mixed effect, we are neglecting the actual nature of the relation between pupil diameter variation and time. Additive mixed models, additive is a family that include linear models, allow to appreciate the more plausible relation between pupil diameter variation and time. And then they are nice because they are mixed effect. So we can estimate our effect of interest, that in this case is the differential impact of audiovisual or visual information on allocation of resource in infants, by cleaning this effect from individual differences due to differences in the diameter of the personal average diameter of an infant compared to another, and also by weighting this effect, for example, not only across with time, but between across with trials, along with trials. So that's why I felt in love with GAMS models, just because they feel more respectful of data, of pupillometry, cognitive pupillometry data, especially. So I'm not, going through the syntax of this model in R is out of the scope of the tutorial, obviously. If you want to write me more information, I can send you. I love to discuss about this kind of model. So whenever you want, I'm just happy to do it with you. And seems very hard to understand, but it's not, because if you're interested in making them in really understanding something, it's worth it to spend some time with it. By the way, the syntax, if you are familiar with linear mixed effect models in R, the syntax is very close, so it's not a big change. And the package I use to run generalized additive mixed effect model is this one, MGCD. And you can find all the documentation because everything is open now. And I just go fastly through the main syntax of this model. Okay, so we have baseline, that is our dependent variable. That is the corrected pupil. We call it baseline. You remember when we corrected in the third degree of freedom. Then we have the familiarization type, that is our main predictor, the factor that we expect, that we manipulated, that we as an experimenter, we are most interested in. Then we have here some smoother terms. Those smoother terms allow us to model the pupil across time, that is the main factor we are smoothing, by familiarization type, by session, so by trials, and by subject. Subject that is specified to be a nesting factor. That basically says, wait, the observations are not independent. And pay attention, because when we run ANOVA and t-student, we are assuming that observations are independent, even in a within repeated measure. This leads to absurd estimation of stuff, and that's maybe a reason why we are in this replication crisis, because our estimations are based on the assumption that each observation in a within repeated measure is independent. It's not, because we have subjects, we have participants, and obviously the observation we have in the final dataset depends, are nested by participants, at least in the easiest scenario. Okay? So.
May I ask?
Yeah, sure.
Because I'm not familiar with this additive models, but what would the difference be or the choice be with growth models that are maybe simpler?
No, it's okay. Yeah, growth model. Okay, our abbreviation of growth model. Okay, I like mixed effect models because maybe just because I start with linear mixed effect models. I like the possibility to specify random effects or something.
In growth curve models, it's exactly the same. No? It's just the same.
Yeah.
It's the generalized mixed effect models, but with different polynomials that fit.
Yeah.
To fit a curve, basically.
Yeah, but maybe in growth models you use statistical like F and T as.
No, it's
the same.
It's the same.
I'm not familiar with that, but I would love to discuss about difference or advantages in using one another. Yeah. The point is, in both cases, you can model across a continuous variable, for example. This. Also with linear mixed effect model, you can use linear continuous predictor, but you are forcing the relation to be linear. So in that case, but yeah. Okay, so we end up with 12 data sets, a lot of uncertainty. And how can we see whether these degrees of freedom during the preprocessing phase indeed had an impact on our statistical results? By launching this script in which you found the model, as I explained. Then an important, the autocorrelation plot for each model, because we expect to have 12 outputs. So no, 12, at least 12 estimated coefficient for the effect of familiarization type. And autocorrelation plot allow us to see whether there is a too high autocorrelation between pupil diameter and time that can actually have an impact on the estimated effect. Then I use the plot diff function to plot the statistical difference, the differential effect between the two levels of familiarization type, audiovisual and visual. And finally, given that we are developmental psychologists, and this is a familiarization, and we are looking at allocation of resources measure, an index of allocation of resources, that is the pupil diameter variation across time, we should expect the first trial to be very different from the last trial. So we expect a reduction in resource allocation as an index of familiarization, right? Sokolov, 1967, already said that. No, we expect in order for a familiarization to be nicely implemented, we should expect attention measured as looking times or measured as heart rate variability or whatever to decrease along with trials, right? This is an index, a classical index of successful familiarization. So I also ask to plot the effect by trials to see if there's if the familiarization actually worked. So let's see if it's the case. There are questions. Where? Oh yeah. First of all, I should create an object called multiverse in which I include all the 12 datasets. Otherwise. No. Okay, it happens, okay. It's quite frustrating, but I mean, we love art, so it's okay. Open tools are like that, you know, sometimes. Okay, so we end up not with one result, but with 12 results. Each, try to. In each row, we see an autocorrelation plot that indicates the degree of autocorrelation between time and pupil. And we have here, in each row is the output, so the differential plot, audiovisual minus visual, and by trial, the plots moved by trial for each data set. So we have the first 5 data sets, the other, so 10 data sets, and the last 2 data sets. Okay, this is an error. So let's go through the interpretation of this output that maybe seems very messy, but with some help is not. First of all, we see that along with the degree of freedom, so in the first case, we have the dataset with all extreme values. We can observe as at first glance that the autocorrelation here is higher compared to the other datasets. Do you agree? So excluding those extreme values reduce the autocorrelation of the model, statistical models, and increase the validity of the statistical, and then as a result should increase the our trust, let's say, in this estimated effects. Yeah.
How do we know which one is all, which one is plausible and?
Yeah, they reflect the degrees of freedom we encountered in this case, but you can arrange it in a better way. I mean, you can, yeah.
The first one is with all the data. The second one is.
Yeah, it proceeds like that. You see, here you have we have the free universe. So he proceeds with all plausible as we created the dataset. All plausible, all AOE, plausible AOE, and so on and so forth. In the same, you can specify the order that you prefer, basically. But in this case, it specifically reflects the steps we did. Okay, but yeah, you can arrange it in a better way than I did. It's up to you. Okay, so we see, for example, this, and this include the first, the third, and the last include extreme values. But the first one, that is the all datasets, that includes extreme values and also includes all the data points, also outside our area of interest, and as the shorter baseline correction, as the higher, so the very first dataset we start from, as the higher autocorrelation. So let's say it's maybe will lead to less plausible estimation. If we look at the differential plot that reflect the difference between visual minus audiovisual, so this is the resulting difference between visual familiarization minus audiovisual familiarization, and we see what that in this first dataset suggests us that there is a decrease of pupil, so a constriction of the pupil in the visual compared to the audiovisual, right? It's a differential plot. Nicely, independently of the autocorrelation and even with some difference in terms of the amplitude and also the standard error associated to the effect, that is how that is signaled by the gray area, the majority of our results indicate the same thing. Apart from this one, so 2 out of 12, 2 out of 12, okay? 2 out of 12 differential effect plot indicate that visual familiarization predict pupil dilation compared to audiovisual. 2 out of 12. The remaining, the majority of models, the majority of data sets instead indicated the opposite. So that audiovisual familiarization induced an increase of pupil dilation compared to visual, the visual familiarization. So we end up with a robustness check, let's say, in which we know that some degrees of freedom may add an impact, but this impact was not so big and allowed this effect to emerge in any case. There are some doubts in your face, so it's not good. Yeah.
Question: would you then bring it like in the ideal case? Would you then report everything? Like, would it 12 pipelines kind of things like mention them? Because like now you have 12 pipelines. What do we do about that? For some, yeah, like what do you at this point?
At this point, I mean, while you are writing up the paper and sending to the journal, I will select the model and the pipeline that show the best fit at the statistical level. So reduce autocorrelation, reduce autocorrelation, or a good fit also in terms of standard error associated to the effect of interest. Okay, put this on the paper and then write, look, in on my supplementary materials, you can have all the data and the script. They show that these results that I'm showing you is quite robust because it's independent on the preprocessing step that I encountered.
Again, give you like the stats of how like the model is
Sorry?
So can the gain after is you applying gain?
Yeah. Yeah.
Give you like the stacks that you like how good the model is.
Yeah, you can evaluate a number of parameters that tells you, sure, for not only for the main effective interest, but also, for example, in this case, for the parameter of each value of time. So you can have an estimation of how good is the fit for each point of the plot, of the plot. Yeah.
Then would you ideally just run thousands of pipelines and check which one is the best?
Yeah, you can, but actually everybody do that already, but they do not share. I mean, you cannot know whether the results that you finally publish is the output of many tries or just one. The point here is not being afraid of the uncertainty, instead embrace it and share it. Because the point is, this, you may say, oh, this is so chaotic and so messy, you can say, and how can you select one result from another, and can be messy for the reader should be, but this already happens. May already happens, no? But we just don't share it.
Maybe someone would just run thousands of them and then cherry the one that is just the best, but then.
Yeah.
I mean, it could be the best for multiple reasons. If you run it, you're always kind of going with extreme cases.
I totally agree with you. But the point is that cherry picking is a bad habit that has characterized cognitive science among other science. Because it also goes with the fact that we do not share our degrees of freedom, our arbitrariness. The uncertainty is there, we decide to neglect it. But is there anyway? This is just a way to be more confident about our results, because we can manage all the degrees of freedom and share with the community. I don't know if, I mean, these problems are there even if you run an ANOVA with just a pipeline. And also, when you publish paper, when you read a paper, you don't know if it was the product of a cherry picking. I mean, but if in my case, if I share with you the data and the script and all my degrees of freedom, then you can actually see and check whether I did a cherry pick or not.
Sure.
You're right.
Yeah. You're showing that you did everything, let's say, so that you showed the process.
Yeah.
But can I ask another question? Because like from the plus doesn't seem to be a huge difference between the processes. Like changing the baseline, for example, that seems to have this huge impact.
Exactly.
Like, do you think like
yeah?
But do you think that it's necessary to do all these? Like if you select a baseline, let's say I select 150 and you select 200, I wouldn't expect to find a difference. But do you think it's necessary to do all of the steps, or just say, okay, I just take a baseline that makes sense, not like I don't know, like something like 100 milliseconds or 100 whatever, and then I don't need to care about 500, 300, 200, 200, because for that you should worry.
Yeah, yeah. I think there's not. There are some degrees of freedom that are plausible and other that are not. But it's impossible to explore the whole multiverse. So I don't think it's necessary to do exactly those steps. Those steps I found it useful, especially in the framework of this study, because I want to be a sense of robustness of the effect of interest in this familiarization in this case. And I come out with these degrees of freedom, okay? But you discussing with another colleagues can be, I mean, it can rise up new degrees of freedom or different, or say, no, the baseline is not important, so let's look at other degrees of freedom with the pipeline. I don't think that those that I'm proposing you are necessary, but are plausible. So can be included. Not satisfied by the response.
I'm just thinking that the different other techniques would be very complex if you have to keep all of these things in account. It makes sense that you want to track all this influence, but it seems to me like one is more a processing question and one is more for a theoretical question about the studies. But one is more find the best pipeline for your data. One is more like your results, and here is all together. It's nice. But
yeah.
I think there's a lot, how you say, there's so many degrees of freedom that I don't know.
Can I answer to that? I think for me, there's maybe a distinction that you're not making, but in my way of understanding this, there's the theoretical, hypothesis-led type of decisions that we have, and then sometimes there's arbitrary decisions because there's some decisions that are not maybe so much based on previous studies, and you do not have a baseline window of, oh, all these studies published and with published no data at all have used 200 milliseconds, so you don't have to doubt that. You can use that, I think, and it's actually more robust using that than actually changing it and looking for the best window for your data set, because then it's going to be much more data specific and not so much hypothesis led, right? At the same time, if you have decisions that are arbitrary, that's what's actually called the outlier analysis or something like this. No? When you decide arbitrarily that you take 3 standard deviations and then you put a footnote saying, hey, if you do it without this, or if you use 2 standard, or if you don't do any outlier analysis, the main conclusions remain the same. We've seen this in many papers. No? I think this is like an extension of this to say, well, it's not only that I put the footnote saying this, but that I put it in supplementary materials and I accept that this decision was arbitrary. It's the same as in the thresholds of attention time. No? Like if this was 20% was the minimum attention time, and sometimes it's very arbitrary. You know, so if you assume that this is not a hypothesis-based but an arbitrary decision, then you can, I think that's the point of this, to say, well, then if you do it in 20, 30, 10, it all leads to the same conclusion, so we accept 20 because of this reason, and continue. In my approach, at least, this is how I.
Indeed, one good degree of freedom that can be even more useful than those that I show you could be that including or excluding participants or trials or flyers point and see how robust the results are. But I totally agree with what you said. And there are nice example in neuroscience, nice project of multi laboratory analysis in which starting from a same data set, different blind groups run their pipeline, their laboratory pipeline, one pipeline, and then come out with 18 different results. So there is a problem. And there's a problem.
But I understand the point. I think it's very good that you are checking all of this. I'm just wondering if wouldn't be best to have like a study that checks this, like one study that makes or try to find the best pipeline having the ground truth, so you can actually check what is happening, and then or do everything every time in your.
It would be ideal. The point is that each design, really the statistical analysis comes not out of the blue. It depends on the design, and we have each study we run, we have a different design, and so it would be ideal to have one pipeline, sure, but it's also to me sounds so impossible, because if you change your question and change your timing or change the age of or cultural stuff, there are uncertainty is there in so many ways that but of course it would be ideal to get a final goal
Definitely there's never gonna be a final answer to everything, right? Like a more structured picture or that.
Yeah, I actually working on something like that. But I agree.
Yeah, I was wondering how you report this kind of information. So like how much you write and how much you just share. As you decide, because then it becomes really long and really long.
There is a nice paper that I will upload on OSF by Stigen et al. And Gelman in 2016 that talk about this, about how to report a multiverse analysis, because it's actually it's difficult to read, but it's not an excuse, because we do science, not games, so it should be difficult in a way. And also you cannot write a book for each study. So ideally, you should report it in the main analysis in the paper, because the interpretation and the conclusion that you write on the results depends on the methodological approach. They are not separated, but the best way you can do it so far, these authors at least suggest that to report the more plausible result and pipeline, and then link the reader to some supplementary materials in order for him to go through it. Yeah.
So would you say we tried different baseline lengths and it was robust enough, and then they can meet just to learn more about each method, and you have to report each of them, and same with, for instance, we just generally say we tested that it's robust, and then that's it.
Yeah, we selected this length baseline. We exclude extreme values, or we include extreme values because our multiverse analysis indicates that is the best pipeline of preprocessing that we could, but the reader could see. So with this, embrace uncertainty instead of fearing it. So not saying I'll try to be perfect doing everything, so I'll be certain. No, you will be always be uncertain. The point is sharing this uncertainty.
Can we do again how you will select then the pipeline here? You will look at the autocorrelation, and so for example, which one would you choose here?
Yeah, so there are some colleagues of mine that are working on a method to come out with some inferential information, some statistical information on the multiverse in order to select not the best, let's say, the more plausible results and pipeline at a statistical level. But Gelman, that is one of the statisticians that start talking about this in cognitive science, this approach, this multiverse approach, prefer to have a more qualitative approach to this. So you have all these plots, all these estimated effects, and you can visualize. And we say visualize is important. It's very important to get a sense of the effect. And in this case, for example, we saw that there is a clear direction of the effect in 10 out of 12 results. So in this case, following Gelman's suggestion, you can just say this: 10 out of 12 different approaches of data show that there is an impact of this on this, and the effect should be this, and this is expected to find again these results in future studies in this direction, because these results seems more independent from my choices compared to another results. Is a tentative conclusion. Also, this is another nice hints that come out from this discussion, could be that we write conclusions based on one study, and it could be not totally scientifically correct to write a conclusion on this. A tentative conclusion may be more humile. But you should not agree with me or Gelmo. But I think it make our theory, our hypothesis, our next step in future studies more confident in a way, or this is what gives to me. I don't know for you.
So here it will be the conclusion. It will stop here, or you will select a pipeline to analyze like the strains, or
that will become a methodological paper. But if you just want to make a claim on the impact of audiovisual over visual, you select the one that you think is more robust for some arbitrary parameters. Again, uncertainty is also in the way you select the one that is the best, and then you can share everything else, and then peer review should do its work and say, maybe a reviewer can say, no, I think that is not the best result, because the best results are shown by the multiverse is another, because you select these parameters to select this pipeline, but another parameter is more, I don't know. And that's why you should be, I mean, during the peer review, it would be very nice to always have a statistician that review our papers in order to be more.
And so you will choose one pipeline and you will do the GAM analysis on these parameters that you choose, right?
Yeah. For example, yeah, it's a possibility.
And so here I would do in the question, which one would you choose?
Me?
Yes, for the visual and audiovisual selection.
In a theoretical paper, actually, I will just say that the audiovisual, in this case, for example, audiovisual familiarization increase resource allocation as expected, because there's a sound, and we have seen at the very beginning that the presence of a sound should increase pupil dilation compared to visual stimuli only, silent stimuli. And this effect is quite robust because it's there even if I apply several degrees of freedom at the methodological level. So from a theoretical point of view, this this result is robust. And okay, this is a part of the story because the experiment here continues with other, we are just looking at 2 participants. So of course here the conclusion cannot be made because we are talking just on 2 participants and 18 trials, 36 trials. But yeah, that would be my conclusion more from a theoretical point of view.
So you wouldn't use the GAM analysis. You wouldn't make GAM analysis in this case.
Yeah.
You would?
Yeah.
Well, and I'm very confused.
Yeah. And GAM analysis, yeah. GAM analysis is just a model that models the pupil diameter along with time and manipulations. I didn't get your.
Yeah, no, I think I here we already.
The multiverse approach is a thing. The GAM analysis is just a model, but you can run a multiverse approach using ANOVAs or whatever.
Yes, I think I understood. But here we would use the multiverse approach to know which pipeline to choose to make the GAM analysis, wouldn't we?
No, because in this case, no, because in this case, in my multiverse approach, there are also GAM models. These are all the output of GAM models. I just tested the GAM over several data sets that are the results of different preprocessing pipeline. But the model is always the same. This is just, okay, now okay, sorry. Maybe it was my fault, I wasn't clear. But the model is just always this one. The data set is a multiverse, so are actually 12 data sets, but the models is the same.
Okay, so this is 12 GAM outputs.
Yeah. This is GAM output. Yeah, sorry, I didn't highlight it. Yeah, sure.
But I have still a question to that.
To them.
You said in the beginning that you would choose the one with the most robust parameters, like these autocorrelation and so on, to report in the paper initially, to get like how big is the difference, for example, between audio, visual, and visual.
Yeah.
And then you say it's robust because 10 out of 12 show it's no different. But how do you choose now the 1 out of 12? So you just look at the plot and look like, oh, this has like the least?
Yeah, the point is that we think that maybe we are mislead. We think that effect size is a number, but effect size are distributions. So there is a confidence of value in which effect size for an effect could be there, because many in different contexts, depending on different stuff or variables, the effect size can vary. So even in ANOVAs, in classical approach, effect size is never a number, it's always a distribution. Here, this distribution can be estimated, but also in classical study with the student ANOVAs, or Cohen 1984, the main paper on effect size, talks about distribution effect size, is never a number. So this is, I don't know if I answered your question, but the point is understanding the limits, the distribution, which are the limits of an effect size, because effect size are always distribution and never a number. Outside the multiverse, I would say. I mean, even in classical statistical approach, we should think about effect size like a distribution. Is not 0.8, but it's a range within a range, always. Accordingly to Cohen 1984. So I think should be. Another question? There was a question?
Yeah. Sorry, I think it's still the same question. You have more analysis, you have a lot of things to say, and then you can't really report all the plots in your multiverse, right?
No, you should not. You should. Yeah.
So which one would you pick right now?
Right now, okay, considering that these are just 2 participants, etc., I will go through the parameters and estimation. For example, if you, I mean, this is a tutorial on pupillometry.
Yeah, of course. But so, in general, how would you go about picking them?
Yeah, for example, you can, it's arbitrary. Yeah. Okay, it's arbitrary. Yeah. As Daniel Lacan say, there's no right answer, but the importance is to justify your choices. So you can select the one that you think is the most representative of the robustness of your results and justify this for some reason. So the autocorrelation plot is a suggestion when you use generalized additive mixed effect models. For example, these models is better from the auto correlation aspect compared to the other models, right? This is an arbitrary selection of one. So in my paper, I will plot just this line, this main effect, for example.
You say the word arbitrary, but I think it's not quite correct, because in the end, all these measurements, like there's some things that are arbitrary, but the fact that you use the correlation values, or you use the fit, the like fit, the big fit, the different values, these are all statistically proven to have some certain representation.
Yeah, but also statisticians do not agree on which one has priority.
But that's very different from being arbitrary. One thing is that it is not 100% agreed, or there's not a consensus, so I explore these or that one. It's very different from saying these are an arbitrary decision. It's not arbitrary. You're basing your decision on many people that have worked on something, right? And then
I
you
didn't
accept a certain degree of margin of error.
Fairness.
That's why
this is not binary.
But I mean, it's very important, I think, because otherwise it seems that you cannot make any decision. You have to contemplate all the possibilities all the time. I don't
they
think
should be plausible, accepted by the community, all the degrees of freedom, and also justify. You have to justify.
I agree.
Yeah, I agree with you. No, I didn't. But at the same time, they are arbitrary in a way that another scientist or statistician could say, yeah, but I would prefer, for example, in model selection, you can decide to use the height value to select all the residual variance. I mean, they all say something a part of the story, but at a certain point, you have to select one parameter above the other. This is in a way arbitrary, but it's not totally arbitrary. I mean,
but it is a little bit naive to pretend that all the field of developmental science, or any kind of field that is not statistics, will be sort of able to evaluate each decision that we make.
Yeah, that's why we need to collaborate with statisticians and methodologists. We cannot say we do science if we not collaborate with statisticians.
But I mean that it cannot be us who are questioning if we have to use the big or the height or the whatever. Like in the end, you can try to understand what are the best parameters, try to use them, and if there's non-consensus about something, then you can do both, compare them, report that you have compared them, etc. But this is very different, because I think sometimes in this direction of Lakens and people that read a couple papers and they sort of put everything upside down just because you think, oh, the p-value was arbitrarily decided in the 80s or whatever, but like in the end, all these decisions have consequences on how we build knowledge, and they are still valid, so to say. Yeah. Even though you can accept or sort of contemplate this variability, but because otherwise it's just impossible. You cannot say anything. You cannot.
But we should discuss at the same time, no? And otherwise, we like, okay, p-value, let's go without understanding or evaluating alternatives, for example, or better ways to investigate phenomena. I mean, it's okay to discuss, no?
No, I'm not saying it's not okay.
Yeah, I agree with that, but I think I'm still not super clear on how you pick your criteria. So very naively, I would have picked the shape that is appearing in the most plots, because that looks robust. Yeah. And then you talked about the autocorrelation thing. Yeah. And then you picked one that has a different shape actually based on that. Yeah. And I'm also not sure why the autocorrelation is.
Yeah, it's not
because in my also naive idea, this is a very stereotypical response, fairly. So it makes sense that it's correlated to itself, right? That one thing predicts what happens next. So I don't really understand how you pick your plot then. Like, what is your criteria?
Yeah, okay. Sorry, it's out. I mean, by the way, it's out of the scope of this tutorial. I would love to do another workshop on that, and we can discuss about it. Because you're right. You're totally right. There are other parameters. I mean, the autocorrelation is one parameter, is not the parameter that by which you decide which results are which outcome is the best out of 12 in this case. There are a number of parameters. It depends of the nature of the model that you are using, but at the same time, for example, when doing a parallel with classical analysis, no? We use 95 confidence interval usually. But why?
Yeah.
I mean, why? Why not 99 or 90?
No,
Yeah, there's no answer. Okay.
I
So,
agree with the approach, but I'm just not sure how to use it. Like right now, I literally wouldn't know
yeah,
how
but
to pick a plot for a paper, very practically speaking.
yeah.
But I think it's a good thing to do, and I'm not saying, you know, it's better to not have plots to pick from.
By the way, you can do the same approach, okay, the multiverse approach, but at the modeling part, in the statistical part, instead of a GAM, okay, that maybe are not so straightforward, or you can also use an ANOVA, okay, and run here, instead of having a GAM model, you can have an ANOVA and still have 12 results based on the 12 dataset model on an ANOVA. And then, okay, I don't know if can reduce the
Yeah, I think I need to think.
Yeah. Yeah.
Because I think I agree, I totally agree with the questions. And I think the thing is that we want to know how to use the multiverse using the GAM. Because with 9 or 12 ANOVA, maybe we would understand how to choose and what to select and stuff. But with the GAM here, I think, like you're saying, for instance, I didn't know if the autocorrelation, I wouldn't have known if a high autocorrelation or a low autocorrelation would be good.
Okay.
And so that's why I think
we can start a collaboration, the three of us. Yeah, I'm serious.
What?
I mean, and go through these details and see which parameters, or yeah.
But I think that's why we wanted to know what you would have done to understand how you would have choose like the importance of the parameter and how you interpret the parameters.
Yeah, I would went through not only the autocorrelation plot, but also through the estimation of the parameters of the effect, because here we have a plot. Okay, I love the fact that this rise at the base. Each of these point plotted here has a corresponding coefficient and standard error associated. Okay, and also another parameter that says how it fits with the model. So I go through this and see the fitting of this, for example. I'll try to show you, but I would like to close the tutorial talking about pupillometry. But I'm very happy that you enjoy the GAMs. For example, here, this is the summary of a model of our data set, okay, of a gamma model of one among the 12 data sets. And we have the estimated coefficient of the main factor or interest, the familiarization type, okay, and the standard error. But also, we have other coefficients, okay, that show us the goodness of fit of the smoother terms, for example. Okay, so this is from one model out of the 12 that we modeled. So by comparing the goodness of fit of those parameters, we can approximately at a qualitative level, because this multiverse approach is a work in progress, is quite, the first paper appeared by Stigen and Gelman in 2016, so it's quite, and still we don't have an indication by statistician. I'm not a statistician, so sorry for that. We don't have a multiverse statistical inference, okay? But there are people that are working on that to answer your question, the right question, to say, okay, but which is the parameter that make us more confident in which model to select? So far, it is why the multiverse is useful. It gives us at least a qualitative impression of the robustness of the results as a function of our arbitrary preprocessing choices.
So you would make a choice and then test around that.
Yeah.
To see that it's robust. It's not that you would test values and then pick it.
By using
the other way around. So you've already made your choice and then try around values around that. Right, correct. Like you decided to do 100 millisecond baseline, but then you test other lengths so that you know that it works.
Yeah, for example, but it really depends on the question, on the design, on it's more, yeah. Gelman talks about a robustness check mainly. It's in a way to face uncertainty and to add confidence in the results. I'm very happy that you get fascinated by the multiverse approach. so I didn't expect it. That's nice. But actually, we can talk about it. I don't know, and think a way to resolve this. It's actually an open problem. So yeah, you're totally right. Okay, so time is running out. We have just 10 minutes left, unfortunately. So just to sum up and to close this beautiful moment. So you see, there are many sources of noise at the design level, at the preprocessing level, and also at the modeling level. So we have 3 levels of uncertainty that we should face if we want to say, yeah, this effect exists, or it's likely to exist. A best practice should be to select the preprocessing step before seeing data. Okay, this is clear. Show and share all the steps in data parsing, all the sanity check, and justify why we select the degrees of freedom. We should talk about missing data and be clear about how we treat them, because they can have a big impact on both metadata about the quality of a study, but also about our statistical results. Baseline correction, how to use it, and if it impacts our results, because we know if we review the literature on cognitive pupillometry applied to developmental infancy research, we will know that there's no a gold standard and no a gold length of baseline, also within the same approach and within the same design. Authors select different lengths based on theoretical or methodological or different aspects. So it's important to discuss the choice behind the baseline correction. The model selection, perfect. Now it tries out, it's important to select which model, because the model that we select give us different information. If we have run an ANOVA, we have different information compared to. This is not better or worse, it's just different. And we should bear in mind that while dealing, for example, with ANOVA, we cannot investigate the effect across time, but just the average effect, for example, because we run average with ANOVAs, for example. And so on and so forth. So the idea is that bear in mind all this level of uncertainty. So how many degrees of freedom in that management? And maybe you would like to continue discussing these also not just with me, but with other people more brilliant than me. And there's a place to do that. It's called Psychostats. I'm a lab manager of this group. That is an interdisciplinary group of psychologists and methodologists and statisticians. And we met on Zoom, and I would love to have you discussing, presenting this group if you like. We talk about pupillometry a lot, but also other measures, other stuff. So please, if you want to continue this discussion that I didn't expect to be so exciting in another context, please write me. And yeah, and we can find discuss the problem that we share together. And I had also this part, so I will upload this about the functional interpretation of pupillometry, but we are running out of time, unfortunately. And clicking here, you will be directed to papers. These are topic that I selected, papers that use pupillometry and talk in detail about pupillometry applied to different topics. In particular, given that you were so interested in gums, I will suggest you this paper that you can find clicking on language processing by Van Rie, that is the author of the MGCV package that implements GAMS. And here it's a brilliant paper that show you more in detail how to evaluate the goodness of it and other stuff about GAMS, given that it's right so much interest. And here, clicking here, you are redirected to some papers, different topics. I would love to discuss with you, but unfortunately, the multiverse was so interesting for everybody that we get lost there. And yeah, and so to sum up, I will thank you and leave you with some tips for a safe trip in cognitive pupillometry. So define a research question very clear, choose a solid design. What it means, solid design, it's better given that complexity and the multifaceted nature of this measure will be ideal to select a design in which we have clear hypotheses about complementary measures, and then use pupillometry as a complementary measure, so as a zoom in some process that is well investigated, well cleared by other indexes. For example, looking times in infancy research, it's an optimal complementary measure of looking times. Then adapt a classical design to the physiological response of pupil dilation, so the latency or the luminance or the gaze shifting, so where present stimuli, etc. Select the degrees of freedom of preprocessing, because we can ignore them, but they are still there. So we can decide to deal with that or not, but they are there. And so select the degrees of freedom of the preprocessing and the statistical analysis based on a specific question, because they are not unrelated. And then when looking at the data, it's important to, in my opinion, to ask yourself some question like, there are physiological artifacts, that is the effect size too large? The latency times from the stimulus onset to the peak of pupillar response are plausible, or the peak of the response is too delayed or too early. And so when does the effect emerge? So sometimes I should expect an effect to be a late effect or an early effect. Is this respected by the pupillary analysis? And then also, what other cognitive process or mechanism am I measuring in addition to the one of interest? Because as we have seen, the pupil dilation respond to many aspects, prior knowledge, physical features. So it's likely that our results are not just talking about the cognitive process under discussion, but also it's a picture of even some other processes. And that's it. So if you want to add some more comments or suggestions, or I hope not to have scared you with this multiverse stuff.
Thank you very much.
Thank you.